I am shooting for a short video on this one. When we think about a collection of gas particles, the collection involves so many millions and billions and uncountable trillions of particles, it's hard to even imagine we could get a handle on the average particle, average speed, that's average energy, etc. But we can in a relatively simple way if we talk about something called the root mean square speed, RMS speed. The root mean square speed is equal to, simple calculation, 3 times the gas constant in energy units, the Kelvin temperature, and the molar mass in, interestingly, kilograms per mole. Yeah, and take the square root. It's not obvious right away where this equation comes from, but it comes from a statistical theoretical analysis of the collection of particles. So in other words, the root mean square speed is the speed of a particle with the average kinetic energy. Because kinetic energy is 1/2 mv squared, the mass of the particle times the speed squared. Because of that, the root mean square speed is a little bit higher than the peak, a little bit faster than the average speed. It is the speed of a particle with average kinetic energy. Since the molar mass is in the denominator, the larger the molar mass, the slower the root mean square speed. That makes a little bit of sense to think that small particles move faster and big particles move slower at the same temperature. At the same temperature and pressure. So it looks like, let me do the root mean square speed of nitrogen and oxygen in the air we're breathing. So if we're in a warm-ish room of 300 Kelvin, temperature 300 Kelvin, and that 3 is the same and that gas constant is the same, I know O2 is 32 grams per mole, and N2 is 14 plus 14 is 28 grams per mole, but I changed to kilograms. We just moved the decimal 3 places left. Well, lo and behold, this relatively simple equation gives us a handle on something that previously we had no idea how fast an oxygen molecule was going. The root mean square speed for a collection of oxygen that we're breathing, 483 meters per second. If I'm not wrong, this is faster than the speed of sound. But since there's no sound at the atomic level, it's just atoms buzzing around, it doesn't really mean much. It means they're going fast. Also means that the lighter nitrogen particles are moving faster than the heavier oxygen particles, and everything in between. What about a lighter gas at a warmer temperature? Here I did methane, so the molar mass is less, and I'm at a warmer temperature. You can get them up towards 1,000 meters per second. It's insane how fast, unimaginable how many there are, how quickly they're going, how often they're colliding. It's mind-boggling, but fun to think about. Calculate the root mean square speed for HBr at a temperature of 26.5 degrees Celsius, given the gas constant in energy units. This was a clicker question at one point in time. Let's just do it. Sometimes it's URMS or VRMS. Depends which author, which text, which paper you're looking at. The root mean square speed, 3RT over molar mass in kilograms per mole. Oh, and so what did we say? Oh yeah, HBr, that's 1 plus 35.45-ish. And oh goodness, that's not looking right. Is this really for HBr? I have 1 hydrogen, 1 bromine. Oh, my bad, chlorine's 35.5. Bromine is 79.9. There we go. So 79.9 plus 1 for hydrogen is 80.9 grams per mole. Change it to kilograms per mole. And oh yeah, so heavy gases move a lot slower. Or you might graph it and ask the same question. Well, which gas has the greatest root mean square speed? This might be the speed or the average speed, the speed of a collection of particles. Wouldn't you say hydrogen gas? Because it's the lightest gas. The lightest gas is moving the fastest, and these are all heavier. And the root mean square speed, remember, is a little bit faster than the average speed. And, oh yeah, now what about a warm gas? So if I warm a gas up, doesn't it make sense to say that the particles on the average go faster? But look also what happens to the broadness or the breadth and the width of that peak. So doesn't it get a lot more spread out? And in other words, the collection of particles has a lot less of a well-defined peak if I make it really, really warmer and warmer, I should say. 2000 Kelvin, 1000 Kelvin, 273 Kelvin, kind of a tall, skinny peak, and the particles just start to go all over the place in terms of their spread of energies and speeds. Wow, that's done. How fast? What? Okay, how many minutes did that take? I'll look it up. Have a good time. Good day, guys, and I'll see you in class. Thanks for all your hard work.